Everyone. So today we're going to start chapter 7. Okay. Chapter 7 is going to be on electron-proton elastic scattering. When I was taking this class, I think, my English was not very good back then still. And these words like elastic and inelastic that usually we don't use every day always confuse me. So I just want to make sure that we have a clear understanding of what we're trying to do this chapter. So last chapter we did a cross-sectional calculations for electron-positron annihilation, and then it decays into muons, but it could decay into other things. But the muon was just shown as an example. We have an E minus, E plus, creates this virtual photon, and then we're going to have a mu plus, mu minus. But in general, actually, if you were to read through the last section of chapter 6, which I skipped because it just got really, really mathy. These can be any fermions, okay? And it actually shows you a result for getting a cross section for any fermion. But then you have to know what the fermion is and then plug in those numbers and stuff like that. Okay. So, but the main thing was that an electron is an elementary particle, positrons are elementary particles. These fermions are quarks or other leptons, right? These are going to be fundamental particles that doesn't have any structures within them. Okay, now we're going to deal with scattering an electron off a proton. And as you know, a proton is not structureless, right? A proton, draw it over here, right? You should just draw this little big circle, right? There's two up quarks and then a down quark, right? 2/3 minus 1/3. That gives me a charge of +1. Right, has a charge of +1. C equals +1. Okay, but that's not all there is inside there. These quarks are actually bound together by these things called gluon, right? And the gluons are not the problem if you're scattering electrons off of it, because the electron does not participate in the strong force, right? So therefore it has no color charge. So it will not directly couple to a gluon, okay? But since a gluon has no charge, okay? But I just made the proton a little bit bigger so I can draw this. What happened is that inside the proton, since you have all these gluons around and the strong force is not, it doesn't decrease, the probability of finding a process does not decrease as you increase the number of vertices. Remember the stuff we talked about in beginning of chapter 6, right? The next and the lowest order calculation and the next lowest order and next lowest order. We can do that with quantum electrodynamics because, right, the alpha factor is 1/137. So every calculation you're going to get 1/137th better. So the first order is already pretty good. The second order will be, get you an extra percent precision. The next order will get you an extra 0.01% precision, right? So doing the first order is already pretty good. But, right, for strong force, since the coupling constant is approximately 1, it depends on the energy involved also. Sometimes actually bigger than 1. What happened is that these gluons, right, there are non-zero, actually pretty large probabilities that these little gluons, actually, let's say you have a gluon that's stringing between this up quark and down quark. This gluon here can actually produce, an up quark, anti-up quark pair, known as the meson. And now, if you're scattering electron off of this, right, not only do you have to deal with these three guys, you have to also have to deal with these, okay? And we're going to talk about how that comes together in the next, not just this chapter, the next chapter also. The hope is that we get you to not to dive, I don't want to dive too deep into calculation like we did in chapter 6, but get you at least enough calculations so you appreciate the fact that a proton is actually a very complicated thing, And how we quantify that is actually using these things called a parton distribution function. So each of these contribution, like, oh, there's two up quarks and then up quark here, right? Because when the electron scatters off of this, what happens is that it actually cares about how many up quarks we're dealing with, right? These are two real up quarks, but then you have a virtual up quark in here, so that doesn't count as a full up quark, right? So what we're going to do is we're going to quantify, oh, when we scatter an electron off of here, how much up quarks are we actually scattering? What fraction of that proton's energy is actually the up quark? What fraction are gluon? In fact, most of them are going to be gluon. What fraction is actually the down quark? What fractions are other quarks that are even heavier? Okay. So that was my long intro to this chapter. I think I was meant for this to be short. And a lot of this work is actually done in this experiment called HERA. I think they've been decommissioned now because they did such a good job that they got all the data they needed, and we have actually very good parton distribution functions when the LHC started in 2008. So I think they ended their experiment, their run in 2007, because they had a certain energy limit, so that they cannot probe certain structures. Where now, with the LHC turning on, you can actually collide instead of electron proton colliding together, which is actually nicer because you don't have to deal with two protons smashing into each other. The LHC, you have two proton and proton collide together at a higher energy. That's the only thing that they like that's good about it, because you have basically one of my instructor when I took this class is that when you collide two protons together, you're essentially throwing one garbage can into another garbage can, and then you have to figure out what the garbage can out is, right? And you're doing this 25 million times per second in order to figure out these high precision measurements that we're doing in particle physics. So let's talk about like a little bit more about maybe a little bit more quantitative and even maybe a little pictures of what we're talking about when we're trying to probe the structure of this proton. Okay, so there are going to be, so this chapter is going to start off with elastic scattering, which is the simpler one. Okay, elastic scattering is when, I'm going to go back to my introductory general physics, is that when you have, let's say, a bumper car, right? And then you have another bumper car, let's say, going in the other direction, right? They hit each other, but they bounce off each other, okay? So in this case, both the momentum and the energies are conserved, right? This is known as elastic scattering. And from teaching physics, this is how I actually learned how the difference between elastic and inelastic. When we teach physics lab, what happened is that we put these bumper cars, but then we put rubber bands at the end of them, and that's why the elastic of the rubber bands, that's what allows me to figure out which one's elastic, which one's inelastic. Okay, but for particle physics, this is when the photon exchange between the electron and the proton has a wavelength that's bigger than the radius of a proton. Okay, what the heck is the radius of the proton? One nice thing about natural units is that the radius of a proton in natural units, actually that's inverse GeV, right, because the link says that, is about 1 GeV, one inverse GeV. Okay, that's about the length of that's the radius of a proton. So if you are exchanging a photon where it's much less than a GeV, meaning maybe like an MeV, 10 MeV, maybe even 100, right? That means this is going to be known as elastic scattering, okay? And that's what the figure 7.1a is trying to show you, okay? Where you have an electron coming in and it comes back out, and you actually do not look at the structure inside the proton. All you care about is kind of like it's a big positive charge, okay? I mean, technically, I think this, if this was happening physically, I think the electron actually scattered towards the photon, but it's okay. Okay. Because of the attractive force between them. Okay. So that's known as elastic scattering. It's also known as coherent scattering. So don't mix, when people swap between these words, don't get mixed up by them. The reason it's called coherent scattering is because it's coherent because all of the entire, all the stuff inside the proton contributes to the interaction with the electron, with the photon equally. So it's not, you're not probing a particular part of it. It's kind of like a one big, let's say you have a classroom full of students, they all shout the same thing. It's like a coherent shout. Okay. So we do this with neutrinos now also, by the way, in case those of you who are interested in neutrino physics, you can actually scatter neutrinos off protons. Okay. So that's the left diagram here. I'm going to talk about it in a different order than the book. I'm going to talk about the rightmost diagram first. Okay. In the rightmost diagram, you have an electron coming in, and the photon is high enough energy that it can actually interact with the individual little pieces of quarks inside the proton. Okay. So inside the proton, there should be 3 real quarks, right? Let's say this one, and this one's the down, or something like that. But the rest of these are actually virtual quarks. Okay. Okay. I don't know why he decided to put 6 in here, but it's fine. Okay. So you can interact with these individual virtual or real quarks because those quarks also have electromagnetic charge. Okay. So this is still quantum electrodynamics because all the interactions are through the electromagnetic force. Okay. Okay. So this is known as deep inelastic scattering. Okay. Deep is in like probing very deep into the proton, inelastic, and that's because what will tend to happen is that you're gonna basically gonna break this protons apart, so it's not gonna be like 2 balls bouncing off each other anymore. Okay. Okay. So in order for this to happen, right, the wavelength of this photon, right, has to be much smaller than the radius of the proton. Okay. In other words, the energy of the photon is much bigger than a GeV. So maybe we're talking about 10 GeV or so. I think that's enough to probe this. So I think the energy at Hera is like 140 GeV or something like that. So it's like hundreds of GeV. Okay, and then when at the Large Hadron Collider, the center mass energy is supposed to be, right, when you collide these two things together, right, it's about 13.6 TeV, a huge number, right, 1,400 times bigger than the GeV. But not all of that energy gets converted into the exchange of this photon. So you only get a fraction of it. Because remember, you're throwing one garbage can full of stuff into another garbage can full of stuff. Okay. And that's what figure 7.1D is trying to show you. Okay. So but then the intermediate case here, I'm just going to lump those together. Okay. Where the wavelength is on the same order of the radius of a proton, meaning the energy of the photon exchange is about a GeV, right? You have to account for the real quarks, meaning the two U's and the D's inside. But what happens is that you don't tend to probe the virtual quarks, okay? Where these virtual quarks are the ones that are being created by these gluon lines, okay? So you can actually see different version, right? By zooming in, but like if you have low energy, you're zooming out very far, so it just looks like a sphere. You look a little bit closer, you start seeing the 2 up quarks and the down quark. You look really closer, right? You start seeing these virtual quarks inside. Okay, so you can actually use different accelerators with different energy to basically probe the different part of the proton.